Step 1. Build a model in Excel. What we mean by building a model in Excel is constructing all the necessary input elements, dependencies and relationships that impact a final set of outcomes or outputs. For example, we have built a frequency, severity model for integrating all the risks from a risk register. The first part of building a model occurs at the level of each one of 20 distinct risks. We have identified its frequency and its severity or impact. Frequency refers to the number of times a risk occurs per unit of time, let's say a year. Severity or impact implies the monetary loss of each event if it were to occur. Thus, for each one of the risks, we construct a frequency dimension and a severity dimension. Afterwards, a special integrative function, called a convolution, integrates these two elements in place. The second part of building a model simply consists of aggregating together all these risks into a sum. Cell D2 on output sheet contains the sum of all the 20 aggregated risks. This cell will eventually constitute the most important output of the model. Notice that this is just one type of model for analyzing operating risk on a company or project. You could build all kinds of models in Excel. A discounted cash flow type of model for evaluating a business venture, a portfolio model that evaluates different types of assets, a credit risk model that analyzes the likelihood of default of a certain credit customer, and the list goes on. The key element here is that, in a nutshell, a model consists of input variables that assume distinct and variable magnitudes, a process that somehow links the relationships and dependencies between these elements and, finally, one or several output variables that are required to be analyzed by the model. Notice that we haven't yet used any one of the IziRisk's ribbon functions. It is important to have a working model prior to it being submitted to IziRisk, where we will, so to speak, place a layer of variability or uncertainty, by primarily replacing input variables from its original deterministic values for specialized IziRisk functions. This is what we do on the next step. Step 2. Distribution functions. Insert IziRisk functions that add stochasticity or randomness to your model. IziRisk Quantum provides a set of discrete and continuous distribution functions depending on the needs. As any Excel function, each IziRisk distribution function has to be written starting with an equal sign before its name. All IziRisk functions are written with the letters I and Z, and then the name of the function. Then, you open parenthesis and add the parameter or parameters required for each function. For example, to insert a normal distribution function that requires two respective parameters of a mean of 100 and a standard deviation of 50, you write it as follows. =, plus I, Z, normal, open parenthesis, then 100 for its mean, comma, then 50 for its standard deviation, and then close parenthesis. Notice that immediately after a distribution function has been created on a cell, IziRisk will generate its respective distribution chart. This feature of showing or not a comment chart for a distribution function on a cell can be enabled or disabled using the distribution charts icon. Hovering on top of cells where distribution functions have been previously written, while distribution charts icon is enabled, will immediately update once you jump to the next cell. Some distribution functions require one single parameter, such as the discrete Poisson function. It only requires its parameter lambda, its mean and variance, in order to generate alternative frequencies with their respective probabilities. For example, cell I5 contains a Poisson function with its single parameter at 2.5. It means that, on average, there may be 2.5 natural disasters per year for this project. With charts enabled, we'd be able to see that there is approximately 8% probability of not having any events, 20% probability of having one occurrence, 25% probability of having exactly 2 events, like 21% probability of having exactly 3 events, and so on. Notice that every single time you hit F9 for recalculation, different random numbers are generated according to the previously defined distribution function on top of each cell with such a function. Other distribution functions require 2 parameters. For example, cell I6 contains a binomial function for subcontractor bankruptcy risk. Given 30 subcontractors on a roster, and a 5% probability of bankruptcy for each one of them, a binomial distribution with those 2 respective parameters will generate stochastic frequencies of how many bankruptcies will be generated for the project. In this manner, there's approximately a 21% chance of no bankruptcies, 34% chance of exactly 1, 25% probability of 2 bankruptcies, and so on and so forth. Once again, by hitting F9 many times over, you will see different random values being generated for this and any other cell with a previously defined distribution function. Continuous distributions are frequently used for risk severities or impacts. Cell N4 contains a PERT distribution for the risk of damage or theft of equipment and tools, that assumes a minimum parameter of $40, a most likely or modal parameter of $50, and a maximum parameter of $200. PERT, by the way, is an excellent distribution to use when you don't have hard historic data to elicit the parameters of a distribution, and can only come by with some expert's opinion. Related to the PERT and a very popular distribution too, the triangular one also uses the same three parameters of minimum, most likely and maximum. Take a look at, for example, cell N3 for the severity distribution of incomplete designs and poorly defined scope. Once all distribution functions have been defined for frequency and severity, column O integrates both components into a single synthesized risk using a convoluted function. We will just mention here that convolution is the adequate mathematical treatment for integrating frequencies with severities in this type of model. If we were to multiply frequency times severity, we'd be making some naive assumptions that are correctly overcome when convolution is used instead. Some software out there may not have this convolution function. IziRisk does. It's important to include convolution. Otherwise, you'd be making gross misrepresentations of risks, especially on the tails of the distributions. In IziRisk, you must explicitly declare which cells are to be considered an input model. In other words, just by containing an IziRisk distribution function embedded in it, IziRisk will not explicitly consider that cell to be an input of a model. Also, this means that you can create models with hundreds, or even thousands of stochastic distribution functions, and, unless explicitly declared, these cells will not behave as inputs in its strictest way. They will certainly generate random numbers during the simulation, but they will not be considered as inputs in their relationships to outputs from a cause-effect point of view. This novel function creates advantages in the treatment of the dependencies between inputs and outputs that we will explain later. Select the whole range I2 to I21. This whole range contains the respective frequencies of the 20 distinct risks on the project. We want these cells to be declared as inputs of the model. Click on the first icon, Input Data. You could go one by one declaring each one of the cells, but it's best to do it from a range. IziRisk will use whatever text column it finds to the right of these input variables as a suggested name for them. In this case, it will be erroneously picking up suggested names on column F. We have defined a temporary range on column AF that contains adequate names for these frequency input variables. Click on the Select Names button to change the reference and type in the range AF2 to AF21. Click on Confirm and watch that now. Names for each one of these 20 input variables are going to be correctly retrieved from texts on column AF. If you were to go now to Show Inputs/Outputs icon, you'd see the existence of 20 new inputs there. Let's do the same for column N that contains severities for each one of the 20 risks. Once column AF has been adequately modified on its text function to accommodate for the names of severities to be declared. Select range N2 to N21. Click on the Input Data button. Click on the Select Names button to change the reference and type in the range AF2 to AF21. Click on Confirm and watch that now. Names for each one of these 20 input variables are going to be correctly retrieved from texts on column AF. If you were to go now to Show Inputs/Outputs icon, you'd see the existence of 20 new inputs there, adding to the previously defined 20 input variables. One last time, we will declare input variables for the total integrated 20 risks on column O. Once column AF has been adequately modified on its text function to accommodate for the names of total risks to be declared. Select range O2 to O21. Click on the Input Data button. Click on the Select Names button to change the reference and type in the range AF2 to AF21. Click on Confirm and watch that now. Names for each one of these 20 input variables are going to be correctly retrieved from texts on column AF. If you were to go now to Show Inputs/Outputs icon, you'd see the existence of 20 new inputs there, adding to the previously defined 40 input variables. So far, we've added 60 input variables for the model. 20 frequencies, 20 severities or impacts and 20 integrated or convoluted individual risks. Step 4. Define outputs. This is the step where we define and name those cells that contain the results that we want to be evaluated. Notice first on column C, that each one of the 20 risks has been categorized into one out of 6 different segments: technical, logistics, environmental, managerial, financial or socio-political. This will allow us deeper analysis for groups of risks. On the Output tab at cell D2, we have placed the aggregation of all risks, which come from column O on Model tab. Every single time we recalculate with F9, we get a different aggregation or sum of all the 20 different risks being randomly generated on the Model tab. Conditional sums by category are also being collected on cells D2 to D8. Therefore, these cells too deserve to be declared as outputs. Select the whole range D2 to D8 on Outputs tab. Then, click on the Output Data button. By clicking on Select Names button, change the reference where the names for these output cells reside. B2 to B8. And confirm. If you make a mistake and declare outputs or inputs that shouldn't be considered, you can always use the second tab for removing outputs or inputs. There, you could choose one by one those outputs or inputs selected to be removed. Be careful, because if you were to click on Remove Output or Input without any previous selection, IziRisk will remove all outputs or inputs altogether. At this point, 60 input variables and 7 output variables have been declared. They can be seen by clicking on the Show Inputs/Outputs button. Step 5. Define simulation settings. At this step, we define important settings required just before a simulation is executed. Settings are modified on the parameter icon. The most important parameter to define here is the number of iterations to be run during the simulation. Iteration is the technical name for the scenario, the recalculation, the F9, the individual instance of a certain scenario. A joint set of iterations make up a simulation. Consider that student versions of IziRisk allow for a maximum number of iterations of 200 per simulation. Professional versions allow for a maximum of 50,000 iterations. In general, you require from 5,000 to 10,000 iterations to achieve a relatively modest convergence on your model. Convergence is the technical term that refers to the relative stability or smoothness of the achieved results. Of course, convergence depends a lot on the required precision of the model. Generally speaking, the larger the number of iterations in a simulation, simulation time increases linearly. That is, a simulation with 20,000 iterations will last as double time as a simulation with 10,000 iterations. On the other hand, precision or convergence is not achieved linearly but marginally decreasing. At first, for example, when jumping from 200 to 1,000 iterations, you will rapidly increase the precision, smoothness, or convergence of your model. But do not expect to increase the convergence of your model when jumping from 20,000 to 30,000 iterations, where marginal increases on the precision of your results tend to become smaller each time. Another visualizing parameter that can be modified here relates to the number of intervals or bins to be used for graphing histograms. You can define any number of bins from 10 to 100 in order to create intervals for your simulation results. Bear in mind that this is just a graphical setting. Underlying data doesn't change regardless of how many intervals you use to group data. However, visualization can change somehow on simulated histograms once you start modifying this parameter. You can also define 2 default percentile values to be located on the histogram, once a simulation has been executed. By default, percentile 5 and percentile 95 are used here. Step 6. Simulation. This is the core process. It's the pivotal point at which IziRisk generates any number of iterations previously defined and sums them all up as a simulation set. Of course, the number of iterations, the number of input variables, the complexity of the relationships between inputs and outputs, the existence or not of convoluted functions, and the status of the hardware being used as a host for this process, will determine its speed and duration. For example, on my personal computer with a Core i5 Intel processor, it took me 7 seconds to generate a simulation with 200 iterations under the student license. 10,000 iterations took 4 minutes and 21 seconds at 38 iterations per second. The simulation can be executed directly by clicking on its respective Simulate button. It can also be triggered by clicking on the Submit button of the parameter Settings definition process. IziRisk will ask whether the user wants to immediately proceed with the simulation. For 200 iterations, 10,000 or any other number up to 50,000 iterations, the simulation process is the same. For each iteration, generate random numbers according to the respective distribution functions, for each one of the cells that contain an IziRisk distribution function on the model. Once these numbers have been drawn, Excel will take its natural course and will recalculate itself upon all the cells in the model. IziRisk will pick up those cells that have been previously declared as outputs and it will store the data on a repository. At the end of the simulation, IziRisk will ask whether you want to save the simulated data, since, up to this point, that data has simply been stored on cache memory. By confirming with a yes, IziRisk will store this newly generated set of iterations, for all previously declared inputs and outputs, in a hidden sheet called Data. Data sheet can be viewed using the simulated data icon. You will see as many rows as iterations have been run and stored. Data will first show columns for as much as 20 outputs, and then, to the right, it will show as many as 100 input variable columns. You can hide the data sheet by clicking again on the simulated data icon. Step 7. Generating and presenting results. Presenting summarized results of the simulation constitutes, obviously, the reason for the whole previous simulation process. IziRisk makes available a number of charts and functions that allow for the analysis and presentation of results. In most cases, you'd have to hover on top of any given input or output variable in order to visualize its respective chart. Hover on top of cell D2 of Outputs tab. Arguably, this is the most important cell of the model, because it encompasses the whole aggregation of project risks. Histogram. Click on the histogram button. Behold the histogram that summarizes your simulated iterations. In my case, 10,000 iterations being generated upon a model created with 60 input variables and 9 output variables, with over 4 minutes of simulation. Statistics are shown on the right side. We can read then, that total risks might amount at a minimum of over $6,000 and a maximum of over $30,000, with an average or mean of approximately $16,000. Its fifth percentile states that there is a 5% probability that the eventual results will be under, approximately, $11,000, and that there's also a 5% probability that they may be over $21,800. Exiting this chart and changing parameters for different percentiles, for example, at the 20th and 80th percentiles, will allow a different placement of the vertical delimiters. Once these parameters have been modified, you don't need to run a simulation again. Click No. And click again on the histogram. New vertical delimiters have now been placed respectively at the 20th and 80th percentiles. Once this chart has been generated, a JPEG file has been automatically saved at the same folder where the model is located. This happens for all types of charts generated. S-curve chart. Cumulative probability charts, also called percentile charts or simply S-curves, allow you to visualize the same information conveyed by a histogram, but with the possibility of comparing multiple outputs or inputs within the same chart. Click on the S-curve button and select all subcategories of risk: technical, logistics, environmental, managerial, financial and socio-political risks. Click OK to visualize the S-curve chart with multiple output risks considered. Environmental and logistics risks clearly appear here to be the largest ones. Y-axis here becomes significant to evaluate cumulative probability. For example, at its median or 50th percentile, you'd be able to view the relative size of each one of the risk categories. Correlation tornado and scatter plot. To rank the different risks of this project, we can use a tornado graph that calculates the linear correlation coefficient between each of the individual risks and the total aggregation of them. Hover on top of Excel model D2 and click on Correlation Tornado. In this example, the correlation coefficient between total risk of natural disasters and total risks is the largest of all, topping the top of the tornado at 0.60. In other words, of all the quantifiable risks, total risk of natural disasters is the one with the highest correlation coefficient versus total risk. Hover on top of risk of natural disasters, cell model 05, and click on the scatter plot icon. See how these thousands of scenarios line up showing a correlation coefficient of 0.60, as stated before on the tornado chart. We could say that the correlation coefficient is a relative measure of how far away all these points are from the best fitted straight line. The closer this coefficient approaches 1, the closer all these points will be with respect to the relationship line of one variable with respect to the other, that is, the stronger its correlation index will be. If the values of one variable change systematically with respect to the values of another, it is said that both variables are correlated. In this sense, as the coefficient approaches 1, we can affirm that there is a relatively high degree of variation in the total risks, when the risks of natural disasters tend to be high, and vice versa. On the contrary, when displaying the correlation coefficient between the risk penalties for labor regulation issues on cell model 017 and total risks, we observe that this index is only 0.05. That is, it is a relatively low correlation coefficient. This implies that regardless of what happens in the risk of penalties for labor regulation issues with high or low scenarios, total risk is not going to be impacted in the same direction in a significant way. In this way, by consolidating the correlation indices between each of the risks and the total aggregate risk, we are able to obtain a relative measure of the importance of each risk when it comes to impacting all of them. These coefficients cannot or should not be added in their interpretation, but they do give us a first approximation, much better than the chromatic classification, to the relative importance of each risk with respect to its total aggregation, statistic functions and risk horizon. IziRisk provides a way for quickly retrieving some simulated statistics of previously defined inputs and outputs. In other words, you don't have to necessarily open a histogram on top of an output in order to read and retrieve its mean or a certain percentile. Functions such as EasyMean or EasyPercentile respectively retrieve on a cell the values of such simulated statistics. Go to cell graph 1 and make sure that cell C1 contains mean. Going back to columns AC, AD and AE, observe that these contain functions that respectively retrieve either a mean or a certain given percentile. In other words, columns AC, AD and AE will now respectively show the mean frequencies, severities and overall total risks for each one of the 20 distinct risks. It only requires you to now change on cell graph 1C1 value to percentile and then redefine that percentile on cell D1, say, at its 80th percentile in order to update the calculated information. Going back again to model on columns AC through AE, we will now be able to respectively see the 80th percentiles of frequency, severity and overall total convoluted risk for each one of the 20 risks. IziMean requires one parameter, a cell that has previously declared either an input or an output and has been simulated. IziPercentile requires two parameters, the first one, a cell that has previously been declared either an input or an output and has been simulated, and the second one, the requested percentile. The risk horizon chart now shows 3 dimensions of risk magnitudes at a single glance. We consider this type of horizon chart a much better representation of ranking risks when compared to a chromatic risk matrix. The horizontal axis shows the severity value, either a mean or a given percentile, of each one of the risks. The vertical axis shows the frequency, either a mean or a given percentile, of each one of the risks. The size of each bubble represents the convoluted magnitude of each risk. Just by glancing at this chart, any decision maker or analyst is able to visualize the relative importance of each risk on the horizon. Some may be high frequency and low severity. Others may be low frequency but high severity. But its relative and most important dimension is being visualized by the relative size of each one of the bubbles on the horizon.